So the first thing is that adding one office hour, okay, on Friday, so 3 p.m. Okay, that is the first thing. And the discussion time right after the class will be maintained. Okay, in case you have you want me to clarify something right away. Okay, that will be maintained, no problem. And I know that I have received a couple of emails during the weekends, but I didn't have time to really didn't have get time to look into that. So if you want, so I will reply to your email by tonight, tomorrow. And if you need more urgent response from me, you can just come to discuss with me. And another thing is about our midterm. Okay, I am thinking about finishing. I'm thinking about finishing chapter 3 before we proceed to midterm. So there are actually five sections, but we're probably only going to talk about 4 of them. But it depends. So the idea is that so that means that I would like to place our midterm on Monday, okay, which is what is 14 days from now. So that should be March 18th on Monday, okay. So it's going to be for midterm. This is our only midterm. So it's going to be like a 2-hour exam. Okay. So it's going to include everything that we have discussed in chapter 1 and 3, from 1 to 3. Okay. Yeah. So any question about this arrangement? No.
It's closed book.
Sorry.
It's closed book.
Of course, possible. Yeah. Okay. You may be asking for things like cheating sheet, calculator. None of these will be used in the class. Okay. So because this is not a class challenging your memory. This is a class challenging your understanding of a system. Okay. It's a branch of mathematics class. It's not for example, a literature class, right? Okay. So I don't want to challenge your memory. And if a formula is hard to derive, okay, it will be directly given, okay, in the exam. So if it's not given, then that means that I am expecting you to either you understand it, or either you can derive it right away. Okay, that's something like that. So yeah. And the range again is everything that we have discussed. Okay, between 1 and 3. Okay, and except for when I'm saying something will not be included. Okay, or we have been diverging from the mainstream of the text from now and then. Okay, these things will not be covered, which means that we should stay very closely to the text on the textbook, and also the difficulty. And the difficulty level of the problems will be very close to the homework. Okay. Cool. Okay, so let's start to talk about chapter 3, which is the discussion of reflections and sources. Chapter 3. Reflection and sources. Okay, and specifically today, I would like to first finish 3.1, which is the diffusion on half line, and then and also some part of the some part of 3.2. Okay, so 3.1. Okay, diffusion on the half line. Oh, by the way, I just want to be sure. I have already uploaded the lecture notes for the last week, right? Right. Okay. Cool. Yeah. In case I forgot to do that. Okay. Cool. So today, what we plan to do, okay, is that you see for the 3.1 is about the diffusion. okay, diffusion equation. So again, let's say Vt, let's not use u's for now. Let's say Vt minus k Vx equals to 0. Okay? Okay, the equation is always the same, and the different thing will be the handling of the boundary conditions. Okay, so what type of boundary conditions have we discussed? So you see in chapter 2, what we have done was something like, so first of all, the whole real line, right? The whole real line. In this case, we are actually not having a boundary condition. Okay, the solution exists on the whole real lines, no boundary conditions in this case. And we have the whole real lines, and we produce solutions. Okay, and also for some restricted case on finite interval. Okay. For simplified case, on the finite interval, we have deduced the well-posedness. Okay, we have derived the well-posedness, and you see, we are hoping that actually we didn't prove that, right? But we were hoping that the well-posedness, which includes the uniqueness, the existence, and the stability of the solution. Okay, let me write it down, not to be lazy. Okay, the existence and uniqueness and stability of solutions. Okay, will also work. First of all, for the whole real line, and it will, we hope the well-posedness that we have deduced, okay, it works for any type of the boundary condition problems, okay, for any type of boundary condition problems. Although we only proved that, okay, it was only proven, okay, in restricted cases or simplified cases. Okay? So this, of course, is not rigorous and actually not a complete derivation of the well-posedness at all. But in this class, this is as far as we can get. Okay? The strict proof, okay, covering arbitrary, the strict proof for the well-posedness for the diffusion equation, okay, and the wave equation for arbitrary boundary condition problems and the initial value problems, okay, that can only be done, well, in my memory, that can only be done after you have finished functional analysis, okay, which is not contained in this class. Okay, so therefore, for that reason, from now on, we are going to pretend that we have already done, we are already done with the well-posedness. Okay, and we will be assuming that that is okay. Okay, that is going to be valid. Okay, for any type of at least for the linear diffusion equation and wave equations, for things that we are going to be looking into. Okay, so that means that we are going to say that we are going to assume that the well-posedness okay, for all diffusion and wave equation from now on. Okay, so this is a compromise. Okay, but this is something that this is a necessary step that we need to take. Okay, specifically, we would like to deal with, okay, you see, we would like to deal with the scenario of half-line. Okay, in 3.1 and the first half of 3.2, okay, we are going to deal with the half-line as the domain of space. Okay, specifically, let's start from the first type of the problem. Okay. Type 1 problem. The type 1 problem of the class class is going to be the following. Okay, so first of all, let me write again vt minus kvxx, okay, equals to 0. And the domain, okay, it was, okay, and when we were producing the solutions on the whole real line, the spatial temporal domain for this equation was something like x and t, okay, belongs to something like from negative infinity to positive infinity, and this actually also should be round bracket, okay, and then multiply from 0 to positive infinity. Right? This is something. This was the domain that we were using, and specifically for the spatial domain, it was the whole real line, okay, which is from negative infinity to positive infinity. And today, what we're going to deal with is another thing, which is xt belongs to only the x only belongs to the positive part, okay, the positive part of the whole real line, which is it belongs to from 0 to positive infinity. Okay, this is the domain for x. And then again, the same from 0 to positive infinity, this is the domain for t. Okay? But when you only talk about the diffusion defined only on half of the real line. Okay, and you may ask, then what about if we talk about the left half of the real line, which is the negative part? And the answer is that will be completely the same, and you're going to see right away. Okay, that will be completely the same as the discussion of the diffusion on the right half of the real line. And the reason is exactly symmetry, which is something that we talk about, we use a lot by today. Okay, symmetry. And yes, so symmetry, let me write it down here. This is the main topic for today. Okay? And since there is not existing on the whole real line for this space, okay, which means that now we need to pose, okay, a boundary condition. Now we need to pose a boundary condition exactly for the starting point, okay, of the solution, which is at x equals to 0. So first of all, let's first define the initial condition, okay, the initial condition, which is that vx0 equals to phi x. Okay, this is for, of course, for t equals to 0. For t, this is the initial condition because it only works for t equals to 0. And the boundary condition, okay, the boundary condition is going to be defined as v0t, okay, equals to 0. Of course, for the diffusion equation on the half line, okay, for a more generalized problem, okay, for the diffusion equation on the half line, then actually, the boundary condition should be richer, much richer than this. So can you please first tell me what type of the boundary condition is this? What type of the boundary condition is this? I am defining what? I'm defining V itself on the boundary. So this is a Dirichlet, right? This is a Dirichlet type of boundary conditions. This is a Dirichlet. This is a Dirichlet boundary condition. And but even in the category of the Dirichlet boundary condition, this is still a very, very specific type of boundary condition, right? Because the most general formulation of a Dirichlet boundary condition should be something like, right? It should be something like v0t, for example, equals to ft, a function, right? But instead of a function, what we are right now is starting from the simplest space. What if the function is simply 0 all the time? Okay, all the time. And what we're trying to do for now is that we will first derive the general solution. Okay, well, not the general solution, but the specific solution for this specific type of the boundary condition. When for a Dirichlet boundary condition, and for v0t equals to 0. And then, okay, the book doesn't tell you to do that, but we might be able to derive a more general form, okay, more general form of the solutions for this more general type, okay, more general type of the boundary condition questions. Okay, so let's start from this. Let's start from v0t equals to 0. Okay. let's start with this. And this has actually a very clear physical interpretation. Okay, this has actually has a very clear physical interpretation. As we discussed earlier, right? Okay, this can be, actually it has at least two physical interpretations. The first thing is that, okay, the diffusion takes place on half of the real line, but the zero, okay, is completely leaking. Okay, zero is completely leaking. Okay, zero is completely leaking. Therefore, the density of the mass on zero, okay, on x equals to 0 is always 0. 0 is always leaking. Okay, so interpretation, physical interpretation. Okay, the first thing is that x equals to 0 is leaking. Okay, x equals to 0 is leaking. And the second interpretation is that this, the second interpretation is that this is actually, we are talking about the heat, okay, on a rod. Okay, heat on a rod, and the rod is represented by the half real line. So this rod is exactly 0 from 0 to infinity. Okay, the heat on the rod. And one end, which is 0, the 0 part, okay? The x equals to 0 is put into a thermal mass. Okay, x equals to 0 is put into a thermal mass. Okay, which satisfy that the which satisfy that the temperature of 0. Okay, and which means that in this case, okay, the temperature of the left side of the rod, okay, is fixed to be 0. Okay, so these are the two physical interpretations, and what you can see that is actually somewhat equivalent to each other. Okay, then the answer is that how do we? The question is that again, how do we produce a solution to for any type of initial condition phi x? Okay, and before we proceed, okay, there is actually an issue over here. There's actually an issue over here. It's actually the requirement. The requirement for phi x, okay? The requirement for phi x. You see, I am asking for what? First of all, I'm asking for a boundary condition that my left side, okay, when x equals to 0, the v should always equals to 0, right? Okay. And I am also saying that the initial condition, which is that when t equals to 0, okay, when t equals to 0, then my initial condition vx0 is a phi x. So the question is the following. Does phi x have to satisfy phi 0 equals to 0? Again, okay, you see, phi x is the initial condition. Phi x is the initial condition. Let me draw it over here. Okay. So first of all, the solution is only defined on the half real line, right? So starting from 0, and this is my x. And we are looking for the solution for any t, right? Okay. So where is phi x? Phi x is over here, right? This is my phi x. And also, I'm requiring what? I'm requiring the boundary condition here. I'm requiring the v0t equals to 0. The question is that, does my phi 0 has to equals to 0? Does my phi 0 have to equals to 0? So those supporting that phi 0 should equals to 0, please raise your hand. Okay. Those saying that phi 0 doesn't have to equals to 0, please raise your hand. Okay, not all students are for that phi 0 has to equals to 0, but also you are not you folks are not brave enough to evaluate, right? And the answer is that phi 0 doesn't have to equal to 0. Phi x, sorry, phi 0. This is the claim, okay, before we should proceed, okay? Claim. Phi 0 doesn't have to equal to 0. Okay, phi 0 doesn't have to equal to 0. And we are going to see that, okay? We are going to see that during the solution, during our solution. Okay, and we'll be doing this at least for twice. Okay, one in the derivation of the solution, and another time when we are looking into our example number 1. Okay, phi x doesn't have to be 0. Then, okay, one may expect right away, right? You see, first of all, if my phi 0 doesn't equal to 0, okay, if my phi 0 doesn't equal to 0, but for any t that's larger than 0, okay, for any t, which means that, so that means that here, for the, I really should do what? I really should modify the definition of the domain, right? To make it doesn't include 0, because if that includes 0, actually, it is going to create some self-contradiction, right? I mean, on phi x and on 0, right? So, but that's a minor thing that can be modified. But you see, if I am saying that phi 0 doesn't have to start from 0, but I'm also saying that for any t to be larger than 0, okay, the boundary condition should be strictly fixed on 0. Then what do you expect on the boundary? What do you expect on the boundary from t equals 0 and entering any t larger than 0? Initially, the boundary wasn't 0. But for any t to be larger, to be positive, for any positive time, the boundary is fixed as 0. It's forced to be 0. Then what would you expect on the boundary? Sorry? Vt equals to 0. What Vt equals to 0? So let me try to say it again, okay? Let me try to say it again.
Vt on boundary. I mean, the derivative of v with respect to t.
So say it again. Which one? Sorry.
Just Vt.
You mean the derivative of t? Vt, that equals to 0. But if that equals to 0, then what would happen? Then that means that my phi 0 is actually my v00, right? My phi 0 is actually my v00, right? And if Vt equals to 0, then actually that
Vt is positive. Vt is positive.
for t is positive, Vt is 0. Yes, of course, that's right. But my question was, what would happen when I'm going from v00 to any Vt, to any v0t, where t is larger than 0? What will happen on the boundary?
All the mass is v.
Sorry?
All mass is v.
All mass. What you're trying to suggest is that all the mass, okay, on the boundary, it should disappear right away. Right, it should disappear right away, and that's actually a very possible interpretation, and we are going to see it. Okay, we are going to see it to see if that is true. Okay, and I can tell you, so that means that there's actually going to be a sharp jump. There's actually going to be a sharp jump. Okay, there's actually going to be a sharp jump on the boundary. Which means that if initially, okay, this is my phi x versus x, okay, if initially it's not at 0, it's something like this, okay, then what would you expect is that for phi x, which is my vx0, right? Now, for a vx epsilon, okay, for a vx epsilon, when epsilon is a very small number, okay, which means that at very small time, what would you expect this function to be like when the time is very small? First of all, the boundary is what? Here is fixed, is directly fixed as 0. Right? This is directly fixed as 0. But what about the place that's away from the boundary? do you expect a very sharp change when we are away from the boundary? I mean, again, the t is very, very small. Do we expect a sharp change when we are away from the boundary? Just think about, let's say, again, there are a lot of water, okay, in this classroom, okay? And initially, the water, there are all water everywhere, and I suddenly open the door, okay? So what would happen is that the water will just go out right away. The water will go out right away, okay? And the density at zero, at the door, is going to be zero. But what about the density that's away from the door? It should be kept almost as the same. It should be kept almost as the same. So what we would expect is that, okay, the place away from it, okay, it's almost the same as before. Again, when my epsilon is very small, okay, for a small epsilon. And the trend is similar when it gets close to zero. But, okay, you see, this function is what? This function should be differentiable. Okay, this function should be differentiable, which means that, this function should be differentiable because we're asking for a vt and vxx, right? This function should be differentiable for any t to be larger than zero, right? Therefore, we would also expect that there is actually going to bend down over here. Right? It's going to bend down over here. This is what we're going to expect on the boundary. Okay, so which means that if we are only looking to the boundary, here, then for the boundary itself, it's actually a sharp jump. It's actually a sharp jump. Okay, directly to zero, from somewhere that's not to zero and directly to zero and kept indefinite. For any way that's away from the boundary, okay, it's going to change gradually. But when you're getting closer to the boundary, okay, the changing, okay, will come early. The changing will come early. Okay, so that might be a little bit abstract, not that direct, right? So let's look into how to solve, okay, this equation in a more direct way. And so this is the issue that we have talked about. Okay, the requirement for this is the issue. Okay, these are physical interpretation and requirements. So now let's start to solve the equation. Now let's start to solve the equation. So again, you see, I have an initial condition. Okay, I have an initial condition, and it is distributed only on half of the line. Okay, it's only distributed on half of the line. And the whole idea, okay, for solving the diffusion on half line was this very specific boundary condition. Okay, v0t equals to 0. Okay, is exactly going to we would like to utilize. Okay, we would like to utilize the boundary condition, which is v0t equals to 0, because you say what type of function always satisfy that. So let's say if we are considering a function on the whole real line, okay, fx on x. If you are considering a function on the whole real line, what type of function would always satisfy that? Because it's going crossing zero. Okay, actually all functions, right? So which means that all function means the following. All function means that f oh, this is going to look backward. F negative x, okay, equals to negative fs. This is the all function. So for example, a function like this and this. Okay, this is an all function. This is an all function. And the idea over here is that since we are already having defined the initial condition phi x, okay, on the right half of the real line, okay, what about we complete the definition of the initial condition on the whole real line, okay, by constructing an odd function based on phi x. Specifically, if this part is my phi x, okay, if this part is my phi x, then the left part, of course, is going to be like, again, it's going to be a negative phi negative x, right? The left part is going to be negative phi of negative x. So that's to say, my f, okay, will be constructed as the following. My fx is going to be constructed as phi x, okay, phi x for any x to be larger than 0, and negative phi of negative x for any x, that's smaller than 0, and specifically 0 for x equals to 0. Okay. Now it is an odd function. It's an odd function, and now, and the good thing is what? The good thing is that now it becomes an initial condition on the whole real line. And if we are lucky enough, then we'll be able to come back to solve a diffusion equation on the whole real line, which we already know how to do it. Okay, instead of only focusing on the solution on the right half of the real line, which is something that we are currently investigating how to do, right? So the first thing is that, okay, using the symmetry, considering the symmetry, okay, considering the symmetry brought by, okay, brought by v0t equals to 0, okay? So we first define an initial condition on the whole real line okay, on the whole real line, which is okay. In the book, it actually defined it actually the notation is phi odd, okay, phi odd x equals to phi x for x to be larger than 0, and negative phi negative x for x to be smaller than 0, and 0 for x to be equals to 0. Okay, this is guaranteed. This of course is guaranteed to be an odd function. Okay, and see, you see, there's another issue, right? Since you see, we have already said that the phi x doesn't have to satisfy that. Phi x doesn't have to satisfy that. Phi 0 doesn't have to equal to 0, right? Okay. Phi 0 doesn't have to equal to 0. Therefore, the odd function that we construct, okay, the fx, we wrote it here as fx, but let's follow the book as to rewrite it as, let's say, phi odd x. Okay, phi odd x. Which means that the function that we construct over here, okay, it might become something like the following. Okay. It might become something like the following. So, oops. Looks like something like here, and here, and here. Which means that, you see here, I mean, the phi x, the positive part, okay, the positive part is always what? Here is always actually always non-zero. And it doesn't approach 0 when it goes to 0. So is the negative branch. It stays away from zero as long as x stays away from 0. But to make sure this is an odd function, we need to fix, okay, phi 0 to be 0. Okay, so far so good. This is indeed, of course, not a continuous function, nor it is differentiable. Okay, it is not. But this is indeed a function. I mean, this is indeed a function, and it's actually an integrable function. We can do integration on that. And you see, because you see, because you see, what did we do to the initial condition when we are trying to solve the diffusion equation on the whole real line? What did we do to the initial condition? What did we do to the initial condition for the solution of the diffusion equation on the whole real line? Okay, so if you still remember, for the diffusion equation, for the solution to the diffusion equation on the whole real line, that was something like, okay, so that was something like uxt Equals to what?
1 over square root of
Okay, so let's say using the source equation. Sorry, using the source function.
s x
That's s, right? X minus y
t.
and t. Okay. And t, and then phi y and dy. Is there any differentiation towards phi? Is there any differentiation towards initial condition phi? No, right? So what is the requirement for my phi, for my phi to make this solution to be valid? As long as it's integrable, as long as we can, sorry, as long as we can carry out integration. Which one is that for you? This? Okay, cool. Yeah. As long as we can carry out integration towards phi, that will be enough. Okay, you see, indeed, this is not continuous, nor it is differentiable. But again, we don't need to differentiate it. Okay, we don't need to differentiate it. That actually seems to be a paradox, right? That actually seems to be a paradox because you see, this is a partial differential equation. For a partial differential equation, okay, to be valid, we need a partial differential equation to be at least, for example, 1 order differentiable towards t and 2 order differentiable towards x everywhere. Right? That seems to be a big problem. Okay, but again, this is for the initial condition. This is for the initial condition, and as long as we are making our definition of the domain doesn't include t equals to 0, then we'll be good. And what we can see is that the issue over here, okay, all the discontinuities over here that we introduced, okay, that is going to trouble us. Okay, actually, later when we see it, it directly comes from the delta function, okay, because of the singularity of the delta function, okay, in the source function. Because don't forget that my s, when t goes to 0, my source function is also what? My source function is also a non-differentiable function, nor is continuous. Okay, so actually, it's not even a function. It's not even a function. Okay, because for a function, we cannot assign a value infinity, okay, to a function. We cannot do that, right? So, okay. Again, the comment is that this is not necessarily continuous nor differentiable. Okay, but we only need phi odd to be integrable. Okay, we only need our phi odd to be integrable, and that is enough. Okay. So now, okay, you see, I have my phi odd. Okay, to be considered as the new initial condition. Okay, and this is the initial condition on what? This is the initial condition on the whole real line, right? This is the initial condition on the whole real line. So now the question is, how do you solve the new? How do you solve the new problem, which is a initial condition, when we're having new initial condition? But again, we come back to the old problem, which is on the whole real line. Okay, how do we do that? Now we just need to plug my phi odd into the formula for the solution to the differential equation, right? So that actually becomes okay. So let's reconsider the following problem. Okay, now it's ut minus kuxx, okay, equals to 0. Okay, for my x and t belongs to now the whole real line and half of the and t to be larger than 0. Okay, And now there's no boundary condition at all. Okay, there's no boundary condition anymore. There is only one initial condition, which is ux0, okay, equals to my phi odd x, and the phi odd is defined as above. Okay? And according to our previous discussion to the solution of the diffusion equation on the whole real line, we are having uxt, okay, the solution should be directly uxt equals to, from the negative infinity to positive infinity, as x minus y t phi odd y dy. Right? This is directly from our previous knowledge. Okay, now, you see, because our motivation was what? I mean, our motivation of creating this new problem and solving this new problem was that we hope, okay, we hope this new solution would be educational for us. Okay, it can help us to derive the solution to the old equation, right? Then what is the requirement for our old problem? What was the requirement for our old problem on only half of the real line? You see, besides the initial condition, of the requirement of the initial condition, we also have a requirement for the boundary condition, right? If we hope, right, if we hope the right half, if we are hoping that the right half of my uxt automatically satisfy can automatically serve as the solution to the diffusion equation on the half real line, then what else do we need to verify? Then now we also need to verify okay, because I'm sorry, our goal is that, okay, our new goal is that we need to verify that my uxt, okay, when x is larger than 0, okay, when x is larger or equals to 0, okay, satisfy is not the best word, okay, can serve as the solution of vxt. We need to verify this, right? We need to verify it. We don't know that yet, but we need to verify this. Okay. Then that means that we need to verify the boundary condition and the initial condition. We need to verify that the boundary condition and the initial condition automatically satisfy, okay, what we have been hoping for the question on the question of the diffusion of half of the real line. Okay. Well, the initial condition satisfies automatically because of what? Because the new initial condition was directly constructed, okay, based upon the old initial condition. But what about the boundary condition? You see, the requirement for the boundary condition is that we want v0t to always equals to 0, right? If I would like to claim that my uxt, the right half of the uxt, can serve as the solution to v, okay? Then what do I need? What do I need to verify for u?
U is odd.
Okay. I also need to verify that u0t, okay, equals to 0. I also need to verify this. So far so good? I also need to verify this. But is that 0? Is that guaranteed to be 0? Based on the solution, is that guaranteed to be 0? Okay, so now let's see. Let's compute what is u, or what is u0t, right? So now u0t, okay, according to the solution, okay, according to the solution, u0t should be written as what? The integration from negative infinity to positive infinity, and then what? As what is x now? What is x now? 0. So there, I mean, the first term only leaves us what? Negative y t, right? And then phi odd y dy. Is that right? Okay. Then what can I say about my phi odd y and my s and my s negative y and t?
Oh, it's the also function.
Okay. For you see, for any fixed t, phi odd y is what? Is what kind of function? A odd function. But what about my s yt, negative yt? It's an even function. An even function multiplied by an odd function is always a odd function. And the integration from negative infinity to the positive infinity of an odd function should always be 0. Okay? So again, this is an even function. And this is always an odd function. So an even plus multiplied by odd, we still get an odd function. Okay, again, this is not for number, right? This is for function. An even number multiplied by an odd number, of course, there's an even number, but we're talking about function, right? Even function multiplied by an odd function, we are still always getting an odd function. And the integration of an odd function okay, will always be 0 as long as we are integrating on the whole real. Okay, so this is guaranteed to be 0. Indeed, this is guaranteed to be 0. Therefore, finally, we can conclude that, okay, therefore we can conclude that Vxt exactly equals to Uxt, okay, for x that is larger or equals to 0. Okay, for x that is larger or equals to 0. Okay? And I mean that is based on the fact that the boundary condition is satisfied by my Uxt. Okay? And there remains one last question. Okay, there remains one last question. Okay, there remains one last question for the last requirement is that we would like to deduce an explicit form of V. Okay. We would like to deduce an explicit form of Vxt, not indirect through the Uxt. Okay, we would like to derive an explicit form for the Vxt. Okay. So, So you see, since we would like to deduce an explicit form for Vxt, that means that you see when we are talking about the U. Here. When we are talking about the U over here, we only would like to obtain the positive branch, and we would like to subtract the negative branch. Okay, we would like to subtract the negative branch. Therefore, we are having, what we are having right here is a, let me see. Okay. What we're having over here is that, first of all, my Uxt, let me rewrite what is my Uxt, right? My Uxt equals to the integration from negative infinity to positive infinity, my Sx minus y, t phi odd, y dy. Again, since we want to deduce an explicit form of V, then we need to get rid of the terms such as the phi odd, because it's something that's based on phi. Okay, we would like to obtain more direct representations of the solutions directly based on phi. Okay, so this can be torn apart into two pieces. The first is the positive piece, right? From 0 to infinity, Sx minus y, t. Okay, here, because whenever I'm choosing my y to be positive, then it's actually the same, right? It's actually the same y, dy. And also there's a negative branch for my y from negative infinity to 0 as x minus y, t, here again, x phi negative y, dy. The negative sign over here, okay, the negative sign over here actually it should be put into the integral. The negative phi negative y is exactly the definition of my phi odd, okay, when the independent variable is smaller than 0, right? So which means that here, when I'm putting the negative sign back into the integral, I'm actually recovering the whole phi odd, okay, in the integral. So that's exactly the same thing. And now changing, we just need to change the variable, right? Here, because you see here everything the integration is from 0 to infinity. Here the integration is from what? Is from negative infinity to 0. Okay. To combine these two integrations, we need to fix the we need to change the integrand to make them to be exactly the same. Okay. So now I'm going to write one more step from 0 to infinity as x minus y t phi y, okay, dy. Here, what I'm going to do is that I am going to change the variable. I'm going to change the variable from negative. Let's say my negative y equals to z. Okay, let's say my negative y equals to z. So you see, when my negative y goes from 0 to infinity, goes from negative infinity to 0, actually my z goes from what to what? Goes from positive infinity to 0, right? It goes from positive infinity to 0. Therefore, I would be able to rewrite the second integral into something like, okay, from 0 to infinity, let's say, okay, so s x plus z t, and then phi z dz. Okay, again, it's only a matter of my selection of the symbol over here, right? Of what I'm integrating inside, what I'm integrating inside over here, right? So I have the liberty to change the z back to y. So finally, I obtain something like from 0 to infinity s, okay, x minus y t, and then minus as x plus y t here, and then multiplied by phi y dy. Okay, that's it. That's everything about it. Okay. First of all, this solution, it only depends on phi y. Okay, it only depends on phi y. And second, this solution is we only need to integrate from 0 to infinity. This is because my phi y is only defined on what? On the positive half, the real line. Okay, and this will only work. Okay, this will only work for x that's larger than 0, larger or equal to 0. Okay, this will only work for s that's larger or equal to 0. And that's of course we can check the boundary condition again. What will happen? What will happen when x equals to 0? What will happen when x equals to 0? This is actually s negative yt multiplied, minus s positive yt. What is this? It's 0, right? Because of what? Because again, my s is a even function. My s is an even function. Okay? So this is the general solution. This is the general solution to the diffusion on the half of the real line, and for a specific type of the initial condition, which is fixed as okay, but the boundary is always fixed as 0. Okay, and let's try to discuss one example. Okay, before we have a rest. Okay, let's try to discuss one example. Okay, example 1. Okay, example 1. Now let's try to solve. Let's try to solve this problem. Solve the same boundary value problem. The same boundary condition problem. Okay, with that my phi x is a constant. It is 1 everywhere. Which means that the initial condition, okay, my initial condition is 1. Phi x, x. It is 1. Okay? Then what is the result? What is the result? Again, I just need to do what? I just need to plug this into the formula. Okay? I just need to plug the new integral condition to the formula. Okay? So that's basically, so that's exactly what, that's exactly, you see, okay, let me put it a little bit smaller. It equals to s whatever minus s whatever, but here the phi is kept as 1. Okay, so it actually disappears from our integration. So I have my uxt, okay, I have my uxt directly equals to the integration from 0 to positive infinity s x minus y t, okay, minus s x plus y t, okay, and dy. So that's good. As x minus yt minus x as x plus yt. You see, this is the integration. This is the integration of s and minus s. Okay, and within the integration, I'm integrating y, so my x is actually a parameter, right? My x is actually a parameter. So that is actually equals to, okay, s from 0 to infinity, s x minus y t dy. And then minus, okay, from 0 to infinity, s x plus y t dy. So that's good. So that's good. And okay, just to get a little bit more from here, okay? So you see here, because my s is what? My s is what kind of function? For a fixed t, my s is always an even function, right? So the first integral, well, can be written as from 0 to infinity as y minus x t. I'm just simply changing the sign. I'm just simply changing the sign of the first entry. Okay, because again, it's an even function. This is what I'm eligible to do that, right? And then again minus s, okay, 0 to infinity as x plus y t dy. Okay, so far so good. Okay, and let me jump several steps. Okay, so let me first tell you what does this look like. First of all, what is sxt? What does an sxt looks like? Sxt is a Gaussian function. Okay, it's a Gaussian function, and the sigma over here, okay, is exactly 2kt. Okay. Okay, sorry. The variance of that exactly equals to 2kt. Okay, the width of this Gaussian function depends on t. Okay, and what is the first integral? What is the first integral? Let's say let's fix an x. And here, because my x should be larger than 0, right? Because this is the solution I'll only have in real life. My x should be larger than 0. Okay, so what is the first integral? What is the first integral? It starts from what and ends at what? It starts from y minus x. It starts from y minus x. Oh, to make it a little bit more direct, let me just say I'm talking about syt. Okay, I'm talking about xyt. It starts from, okay, when y takes 0, it starts from somewhere that's negative x, okay, and goes to infinity. Therefore, my first integral is this. So good. It starts from here. It starts from here and includes everything on the right hand side. What about my second integral? You see, what about my second integral? Okay, here and here. Okay, and the same del curve. Forgive my drawing. What about my second integral? Okay, and now instead of negative x, now it actually starts from certain positive x, right? So the place over here, okay, this was negative x. Now we need to start from certain positive x. And ends at what? The integration starts from now and ends at what? Starts from here and ends at infinity, right? So it's this. Now the result is the first integral minus the second integral. So what we left? Okay, so this is actually the negative from negative x to positive x. Okay, negative x to positive x s y t dy, which is exactly. Let me use another color, which is exactly what's left, which is exactly this. And this is what is left. Okay, that's white. Okay, now now we are able to discuss the boundary again. Okay, now let's revisit the boundary. Okay, now let's revisit the boundary. To revisit the boundary, you see. Specifically, we care about the chain. We care about the shape. Okay, we actually care about the shape of uxt. Okay, when let's say first of all when t equals to 0, and when t is small, and when t is large. Of course, t equals to 0 is this. This is my ux0. This is my x. Okay. Can anyone tell me what will happen when t becomes? Let's see. What will happen when t becomes large? What will happen when t becomes large? So first of all, let's say okay. Let's not say t is small, t is large. Let's just say positive t. Okay. Let's just say positive t. And what we are doing right now is that. Here, I know that my uxt is exactly the integration of syt, okay, from negative x, from y equals negative x to y equals positive x. Specifically, is this. Okay? That means that when we are fixing a t, let's say we fix a t. We fix a t and we are changing the x. What is u0t? Again, what is u0t? If we are talking about u0t, that means that my x equals to what? 0. So this integration contains what? Nothing. This integration contains nothing. It starts from 0 and ends at 0. It contains nothing, right? So it's going to be which means that here my uxt is going to start from here, right? Indeed, it satisfies the boundary condition. And when my x starts from 0 and becomes larger and larger and larger, that means that initially the integration only contains this, which is nothing, right? But now it will becomes larger. When x becomes larger and larger, the integration will contain more and 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 more, right? The integration will contain more and more and more. What will happen when my x is a very large number? When I'm fixing the t, what will happen when my x is a very large number? When x is a very large number, that will almost be like the integration from negative infinity to positive infinity, right? So what is the integration of the source function from negative infinity to positive infinity? 1. That's 1, right? Okay. So when x is very large, it should actually get very close to 1. Okay? And you see when this gradually grows, when the x gradually goes from 0 to be very large, it's actually a continuous process to include more and more and more and more places in the integrand, right? Okay. So that means that I am having my solution as this. is going to be a curve approaching 1, but never really reaches the 1. Okay, but never really reach the 1. When x becomes larger and larger, okay, so probably better for me to rewrite the uxt. So here, my uxt. This is going to be my blue curve is my uxt. Okay, blue curve is my uxt. Okay, so far so good. So far so good. Now the question is that what will happen when t is very small? Okay. What will happen when t is very small? Let's say ux epsilon. What will happen for my t is very, very small? When my t is very small, I know that the variance or the width of the bell curve depends on t. So the width of the bell curve should be what? Should be very, very narrow. Okay, it should be very small, and my bell curve should be very, very narrow, right? Which means that I'm going to look into certain things like this. Okay, I'm going to look into things like this. Right? This is the shape of my this is the shape of my S x epsilon. Okay, this is the shape of my S x epsilon. And the same thing, what can we say for u x t? Oh, sorry, for my ux epsilon. What can I say for my ux epsilon? Again, when x equals to 0, indeed it contains nothing, right? It contains nothing. But now when x is becoming larger and larger and larger, what can I expect? You see, the integration is again from negative x to positive x, right? And it contains everything over here. It contains everything over here. But this time, the integration is going to cover the majority of the mass in a much faster way, right? This is because the bell curve is now becoming much more narrow, right? So the same x, but when we are reducing the t to be a much smaller number, okay, the integration will be much closer to 1. Is that right? The integration will be much closer to 1. Do I need to repeat what I just said? Okay, so again, you see, first of all, when my t is very small, okay, the width of the bell curve, the variance of the bell curve, sigma squared equals to 2kt, okay, that depends on t. So the larger the t, the larger the width, the smaller the t, the smaller the width. When my t is very, very small, I would expect the bell curve to have a very small width, which means that most of the mass, most of the area, it actually concentrates around x equals to 0. Okay. Now, I'm fixing the x. If I fix the x and reduce the t to an epsilon, then that means that this integration will actually include much more mass. Because again, most of the mass centers around 0. Okay, centers around 0. It's much easier for me to include most of the mass right now. So far so good? So far so good? Therefore, I would expect the same x, okay, for the same x, okay, now it becomes much closer to 1, okay, much earlier. Again, it's also approaching 1, but okay, it's now growing up in a much faster way, around 0. Okay? Any question about this? Any question about this? I hope not, right? Okay. And okay, one last discussion before I release you folks. Okay, to the break. Okay. Now again, let's stare at this again. Okay, let's stare at this general solution for xt. Uxt equals to from negative x to positive x as uxt. Okay. What would happen when I am taking my x equals to 0? What would happen when I'm taking my x equals to 0? What would happen? Sorry, let me use another one. What would happen when I'm taking my x equals to 0? Yeah, when t equals to 0. What is s yt when t equals to 0? What is the source function when t equals to 0? Delta function. So I'm going to repeat everything that I just said, okay, with regard to the delta function. So now I'm talking about not even a small t, okay? I'm directly talking about, okay, sx0. My sx0 should satisfy that it's 0 everywhere else, but, okay, it's infinity over here. It's infinity over here. Okay, which means that all the mass is around, it exactly, okay, all the mass exactly locates at 0. Okay. Now, what can I say about the solution? uxt. Now you see, I don't need a positive x to include all the probability, or to include all the mass anymore. Because of what? Because again, this is a delta function. As long as I am integrating at 0 when x equals to 0, or x equals to any positive number, I'm integrating from what to what? I'm integrating so from here to here, from here to here, from here to here, from here to here, from here to here. But for any choice of my x, you should directly equals to what? 1. Should directly equals 1. Again, this is because for the delta function, my x0 equals to delta x, okay? For my delta x, it satisfies that, okay? All the mass, okay, okay, it exactly locates at 0. Therefore, the integration will be 1 for all the choice, okay? The integration will be 1 for all the choice of my x, and which is this, which now satisfies the initial condition that we posed earlier. Okay. So that's everything that I would like to talk about for section 3.1, and let's take a 5-minute break and then come back. Oh, sorry, this is not everything, but anyway, yeah. continue. So we have just derived, we have just derived a general solution to a very specific type of boundary conditions of the diffusion on the half wheel line. Okay, and don't forget. Let me rewrite. Okay, let me rewrite what we have just done. So again, we have been doing. We have been doing Vt equals to minus kvxx equals to 0, and for the initial condition, it was Vx 0 equals to phi x, and for the boundary condition, it was V0t always set as 0. Okay, so this is again a Dirichlet. The Dirichlet boundary condition. Okay, this is the Dirichlet boundary condition. And the method that we used was the symmetry. Okay, the method that we used was the symmetry, using the symmetry. Okay, introduced by the boundary condition, because the boundary condition fix the boundary condition always fix the boundary at 0. So we instead, so we are designing a new problem, okay, and assuming everything starts from an odd function, and which will actually let the solution always stay odd. Okay, so the idea, so then we start from an odd function phi odd, okay, and then all the uxt stays odd. Okay. Now we are using the similar symmetry method, okay, but for another type of the boundary condition. Okay, so everything stays the same. This line, okay, this line and this line will stay the same, but I'm going to change to another boundary condition. I'm going to change the boundary condition that, okay, my Vx at 0t equals to 0. So of course, this is not a Dirichlet boundary condition, this is a Newman boundary condition. Okay, this is a Newman boundary condition. So that is to say, on the boundary, okay, on the boundary, this is my t, this is my x. I have my initial condition over here, okay, and I'm having my boundary condition over here. Now, the boundary is not kept as 0 anymore. The boundary is not kept as 0 anymore. Instead, we are keeping the derivative at the boundary. We're keeping the derivative, the first order derivative at the boundary to be 0. And we are fixed so which means that we would expect our uxt to be always something like this. Okay, to be always something like this. Okay, this is for x equals to 0, and it's always something like this. Okay, at the boundary, the derivative is strictly 0. Okay, it's always strictly 0. Okay. Well, first of all, again, our first goal is to give a first issue is to give a physical interpretation. Okay, is to give a physical interpretation. Okay. What can you say for Vx to be set as 0 on the boundary? What does it represent? What does it represent? In a diffusive system, what does the first order derivative represent? The velocity of the flow, or the amount of the flow going through certain x, certain location, right? Don't forget the fixed form, right? Don't forget the fixed form, right? For the diffusion, considering this is the tube, right? Considering this is the tube, then, okay, the flow depends on the differences, or the flow depends on the differences between the density. Okay, and when we are taking the limit, it's actually it depends on the sign and the magnitude, okay, of the derivative Vx. Okay, so Vx set at 0 on the boundary means what? On the boundary, there's no flow. Right? This means that on the boundary, there's no flow. Okay. What kind of system can you design to ensure that there's no flow on the boundary? Okay. The answer is that this will work for a reflective boundary. Okay. This will work for a reflective boundary. What does a reflective boundary mean? That means that, okay, any of the flow, again, this is my boundary, any of the flow going to this place will be bounced back. If I imagine that I'm a particle, okay, imagine I'm a particle, okay, because previously I was saying that, okay, I'm going out and I'm going back. Okay, that works for Vx, sorry, that works for V0t over 7, 0, right? Now the particle goes to this place and going to be bounced back exactly with the same velocity. Okay? Then why this will guarantee that there is no flow at the boundary? This is because you see any of the flow going this way will be bounced back in this way. Right? Which means that the flow going in on the boundary, the flow going on this way, okay, will also incur a flow going out with exactly the same speed. Right, so the net flow is going to be 0. Okay, so a reflecting boundary means that the flow on this direction will equals to the flow on this direction. Okay, so the net flow is 0. Okay, the net flow is 0, which means that now we can guarantee that my Vx 0t equals to 0. Equals to 0. Okay. So now, you see, again, we are asked to solve the new problem. Okay, with the new boundary condition. And you see, previously we were using and we proposed to exactly use the same, not to exactly use the same method. Okay, but we are hoping to use exactly the same idea. Okay, we were using the symmetry. Okay, we were using the symmetry because the symmetry allows us for what? The symmetry allows that. Okay, because if the function has to go through 0, then if I flip it and flip it again, okay, then I am guaranteed to obtain an odd function. Now, it is not the boundary is fixed at 0, but the derivative at the boundary is fixed at 0. If we also would like to utilize a symmetry, now what kind of symmetry should we ask for? Okay, because previously I was doing what? I was doing that I'm actually rotating the function for 180 degrees, right? Because if it's fixed at 0, it will always be fixed at 0, right? Now it's not fixed at 0 anymore. This place, it can be high, it can be low, it can be high, it can be low, but it always satisfied that, well, it's always satisfied that the derivative at the boundary condition is 0. Okay? So what kind of symmetry can we use? The mirror, not the rotational symmetry, but the mirror symmetry. Okay? Because if I mirror the right hand side, mirror the right part, okay, to the left part, okay, it will, of course, will always take, it is going to, well, first of all, it's going to be an even function. And this even function is actually what? It's actually differentiable. This even function is actually differentiable around 0 because it will keep the right part is the derivative equals to 0, and now the left part will also give rise to the derivative to be 0. So the derivative on the both sides will be kept as the same. Okay. So now our new proposal, okay, is to design a phi even. Okay, is to define a phi even x that equals to phi x for x to be larger than or equals to 0, and my phi negative x, okay, for x to be smaller than 0. Okay. So that's good. And everything else is going to, everything else will exactly follow what we have done. Okay, everything else will exactly follow what we have done. Because of what? Because you see, so this now the new phi even x is again an initial condition defined on the whole real line. Okay, so I am able to turn to, so now the new problem, okay, the new problem. Again, it becomes phi t minus k, ut minus k uxx equals to 0, and ux0 equals to my phi even. Okay, my ux0 equals to my phi even x. So good. And of course, my uxt, okay, will just become from infinity to plus infinity as x minus y, sorry, t, and then phi even y, dy. Right away, okay. But before we exactly use the solution u on the whole real line, okay, to represent the solution to the reflective boundary condition on only the right half of the real line. Okay. Again, there is one more point we need to verify, right? We need to verify that my ux 0t is indeed always 0. Right? I need to verify that. So that's good? I need to verify that. What is that? Exactly, what is that? How do I compute ux0t? This is my u. How do I compute its derivative? It's estimated at 0. I can just, again, I'm entitled to switch the order of differentiation and integration as much as we want. Right? Okay. So now I'm computing my ux, okay, xt, evaluated at x equals to 0. That should be, okay, first of all, from negative infinity to plus infinity, I'm going to, because initially I need to differentiate the whole thing, right? I need to differentiate the whole thing with respect to x. Okay, I'm now just changing the differentiation, put the differentiation inside the integration. So what I have here is actually, okay, ds x minus y t phi even y, okay, dx dy. It is this. Again, y has nothing to do with x. So this is actually from negative infinity to plus infinity. Okay, so s ds, okay, x minus y t dx phi even y. Of course, this is actually choosing x equals to 0. This is again choosing x equals to 0. Right? This is choosing x equals to 0. So that's actually from negative infinity to plus infinity s x negative y t, okay, dx phi even y. Okay? So again, Also, I missed a dy finally. dy. Okay, this is an integration with respect to y. First of all, phi even y is what kind of function? Even function. My s is what kind of function? My s is what kind of function? Even function. The derivative of an even function is what kind of function? Is it always an what kind of function? Odd function, right? So which means that this is always an odd function multiplied by an even function. And the integration and the multiplication should be what kind of function again? Odd function, right? So this is again an odd function, again the integration of the odd function is going to yield 0. Okay, it is indeed 0. So after the computation, I have already verified that indeed, okay, the boundary condition is satisfied. Okay, the boundary condition is satisfied. So it is legal. Okay, so it is legal now to use this. Okay, this as long as my x is larger than 0, larger or equals to 0. Okay, the right half of my ux to represent the solution to the reflexive boundary condition. Okay, and again, the final step is to derive. The final step is to derive an explicit formula for that. So, I mean, I'm going to save it for. You can just verify it by yourself, but I'm going to write down the answer. It's going to be my vxt exactly equals to from 0 to infinity. Okay, from 0 to infinity. Okay, sx minus y t, and then plus sx plus y t, okay, and then multiplied by 5y dy. Probably using the square bracket over here. Okay, just to compare with the following solution. Sorry, with the previous solution, it was s minus y, sx minus y minus sx plus y. Okay, this is to do what? This is actually to obtain. This is actually going to obtain canceling what? Canceling the boundary. Okay, canceling the boundary to make sure that the boundary is strictly 0. Now, what we are having here is x minus y t plus x plus y t. Right? This is not canceling the boundary itself anymore, but canceling the derivative on the boundary, right? Because this will, if you are choosing x, okay, if you are choosing x, the derivative of this part and the derivative of this part is going to cancel each other. So what's it do? Because of what? Because one part, the derivative of s, when I'm choosing x equals to 0, right? The derivative of s negative yt is actually approaching a certain place on one direction, and this is approaching the y on the other direction. Okay, so they will automatically cancel each other. Okay, so this is everything for 3.1, and we have discussed the specific solutions. Sorry, the two solutions to two different types of the boundary conditions. And one comment I would like to provide is that, okay, before we proceed to 3.2, one comment I can provide is that, you see here, the solution that we are having over here, this is for, okay, so yeah, let me just put it here. Okay, this is for the boundary condition that u0t equals to 0, right? This is for u0t equals to 0. Okay. Now, I just said that this is indeed, of course, this is indeed a Dirichlet boundary problem. Okay, but this is far from the general case, the general scenario of the Dirichlet boundary condition, right? If I would like to extend this just for only a little bit, what can you do? What can we do for a u0t not equals to 0 but equals to certain c?
Oh, we just define a new function like ux t minus.
Sorry, say it again.
So define a new function like xt minus and.
Very nice. Yeah, very nice. Yeah. Yeah. You see, if now I am fixing the boundary not as 0, but as another constant, okay, another constant c, okay, now what we can do, what we can choose to do is that now let me define, okay, now let's say, now let me define, okay, let's say a w, okay, a wxt, okay, which equals to, let's say, uxt minus c. First of all, we need to verify that my wxt, okay, is still a solution to the diffusion equation, right? Is that true? Is that true? How do we verify that? How do we verify? Again, first of all, it's linear, right? Everything is linear over here. And what is the time derivative and spatial derivative of a constant c? It's 0. Both of them are 0, right? So indeed, my w is still a solution. That's still a solution to the diffusion equation. I'm going to be a little bit lazy over here. The DE stands for the diffusion equation, okay? It's still a solution to the diffusion equation, okay? But what kind of boundary condition does this satisfy? What kind of boundary condition does my W satisfy? What kind of boundary condition does my W satisfy? U satisfy that the boundary is always C. My W equals to U minus C, so my W will satisfy that the boundary condition exactly is 0. And we will be able to utilize whatever that we have done, okay, whatever that we have done to solve, okay, my W, because my W is satisfied. Okay, this is because my W0t is exactly 0. Okay, so this becomes our type 1 problem again, and I will be able to directly solve what is W. And whatever W it is, by adding a C, that's going to be my U0. So that's going to be my my solution U that satisfies the boundary condition as C. Okay, but this is beyond the book. This is indeed beyond the book. But that's such a straightforward, okay, such a straightforward colloquially. Okay, so it will be a pity if I don't really touch that. Okay, well, yes, sorry. Okay. Don't forget that's the okay. That's the type 1 problem, and this is type 2. This is the type 2 problem. Okay, type 2 problem. Okay, so now, what kind of extension that you can think of for the type 2 problem? For the type 2 problem. For the type 1 problem, we were just saying that we have solved the case for the boundary is set as 0. Okay, now we extend it to the boundary not as 0, but keep us as C. For the type 2 problem, is the derivative. Okay, is the derivative set as 0. Okay, is the derivative set as 0. But again, this is a very, very specific type of Newman boundary condition. So, what kind of extension that you can think about?
Maybe like ft equals to ft.
Equals to what? xt? ft? ft, well, that's, yeah, I mean, of course, that's an extension, but that could be a little bit too general. And I can tell you why I don't like that, okay? So, the generalization that I'm considering for now is, something like, okay, Vx0t, okay, instead of always 0, now it is always something like, for example, it's always, again, a C. Okay? The boundary condition is always a C over here. Okay, now, what can you do to solve my V for this new boundary condition? Again, I'm going to define a W, T, Wxt. Of course, based on V, xt, but of course, adding something. what can I do to change the new boundary condition to the old boundary condition that we have just talked about? You see, the new boundary condition is that the derivative on the boundary is fixed as c. What can I do to switch it to the old boundary condition whose derivative is always fixed as 0? What we have been doing before was to directly subtracting a constant, because a constant can help us do it, right? Now, instead of a constant, what can you propose to add or subtract?
Minus CS.
This is the most straightforward thinking, right? Minus the CS. Minus the CS. Because you see what? Because you see my v satisfy that on the boundary. Okay, on the boundary, the derivative is c. My negative cx satisfy that on the boundary, its derivative is what? Negative c. Okay, its derivative is negative c. So now my w again will satisfy this old boundary condition. But there's again one more step we need to verify. Right? I need to verify that my w is still a solution. Still a solution. Okay? My w is still a solution to the diffusion equation. Is that true? Is that true? Why that is true? Because cx, of course, on t direction, the derivative is 0. But c is a linear function, so its second order derivative is what? Its second order derivative is 0. So again, my cx, okay, my cx satisfy that my cxt equals to 0, and my cx xx is again 0, which means that the new constructed solution, w, is still a solution to the diffusion equation. Okay, which means that I am now able to directly solve my w, okay, with the method that we just introduced. Okay, and now going back to and finally we can come back to solve, okay, the equation w. Okay, so we're having last 5 minutes. We're having last 5 minutes, but I think with so much discussion over here, I think we are able to start the discussion for the reflection. Okay, now the reflection of waves. Okay, 3.2. We only have 5 minutes, but that's enough for us to set up the problem and then talk about what is the idea. What is the idea of solving the problem? Okay. Yes, go ahead.
It should be 0.
Sorry.
The last BXT. No, the red line. The integral is from.
Oh, yes, definitely. You're right. Reflection of waves. Okay, and the wave equation. Okay, the wave equation that we are talking about over here is, again, let's see, VTT equals to c squared VXX. Okay, and for xt, it belongs to from 0 to infinity and from negative infinity to positive infinity. Okay, I didn't write this thing reversely. This is actually the right position. Because, first of all, for t belongs to any real number. We have discussed this, right? Because the wave equation could be evolved forward, either forward or backward. Okay, so my t can go to negative. It's okay to evolve the wave equation backward. On the other hand, in this case, I'm not talking about the wave on the whole real line anymore. I'm talking about the wave only on, again, half the real line. Okay? So this is the wave equation. This is the wave equation. Wave equation on half real line. Okay? And there are two pieces of initial conditions because now the time derivative is now order 2, okay? The time derivative is order 2, so now I need two pieces of initial conditions. I'm having my Vx0 set as phi x, and my vt x0 set as psi x. Okay, again, this is for t equals to 0. This is for t equals to 0, and x belongs to 0 to infinity. And the boundary condition is again set as v0t equals to 0. This is for x equals to 0, and my t is anything from negative infinity to positive infinity. So is it good? Okay. So based on what we have done, okay, how do you expect to solve that equation? Based on what we have done, how do you expect to solve that equation? Again, this is a Dirichlet boundary condition problem. Set as the boundary is always set as 0.
Oh, so just change the initial condition P as say 5x to be all function.
We just need to again create the new all function, the new initial condition. So we are going to create. Where's my pen? Okay. Well, we are going to create, okay, my phi odd, okay, again equals to phi x, negative phi, negative x, x is larger than 0, x is smaller than 0, and 0 when x equals to 0, and same reason, the psi odd, okay, x equals to, okay, psi x for x be larger than 0, 0 to for x to be equals to 0, and negative psi, negative x for x to be smaller than 0. That's it. Okay, again, this is a new initial condition. Okay, this is a new initial condition. And what we need to do is to guarantee that, okay, that now it starts, now we are recovering this problem, okay, originally from a wave equation on only half the real line, now extended to the wave equation on the whole real line. Okay, as long as we can guarantee that my ux, okay, so now let's say I'm talking about a new problem, okay, which is that my utt equals to c squared uxx, okay, and now my xt, okay, is now belongs to the whole real line and whole real line. Okay, and now my initial condition is that my ux0 equals to phi odd x, and my utx0 equals to psi odd x. Okay, this is the new problem. So I'm setting up the new initial condition, and this is the new problem. Okay, and my goal is that we can use the new problem. We can use the solution to the new problem and just cut it by half, and we'll be able to recover, okay, the solution to the original problem that we cared about. And indeed, there's one more thing that we need to verify. So before we move back to the original problem, what is the solution? What is the solution to u, xt? What is the solution to u, xt? Based on, yes, go ahead. 1/2, okay, phi, okay, phi odd, x plus ct, and then plus phi odd. Yes, go ahead. X minus ct, and then what? Plus 1 over 2c, right? The integration. Well, I'm cheating because I have the book. And x minus ct and x plus ct psi odd. Y. D. Y. So that's good. And here again, we need to verify. Okay, we first need to verify. Okay, we still need to verify that my u0t still equals to 0. Right? Because that was the requirement for my old problem. That was the requirement for my old problem. If I would like to use the solution to the new problem to represent the solution of the old problem, then actually they have to consistent with each other. in the solution, right? Okay, but is that true? Is that true? What will happen when I'm taking my x equals to 0 over here? This is phi all ct plus phi all negative ct. First of all, what does phi all satisfy? What does my phi all satisfy? My phi all is what kind of function? By design, my phi all is what kind of function? It's an odd function, right? So phi all ct plus phi all minus ct is what? This one, in the bracket is what? 0. Okay, now, again, my x is 0. So this is an integration from negative ct to positive ct. I'm integrating what? I'm integrating another odd function. So this is indeed in the integration from here to here. What is the outcome for this integration? Again, 0. So this is going to be 0, 0, and my uxt, therefore my u0t is always 0. Okay, so is it good? So yeah, so that is the wave equation on the half of the real one. Let's see if there's anything else that I can talk about really quickly. Probably not. Okay, so I'm going to stop here. So yep. So the our goal is to finish. Our goal is to finish the whole chapter 3 by the next Monday. Okay, including the next Monday, and then we'll get into something about chapter 4, but that will still give you enough time. Okay, to review everything that's between 1 and 3. Okay, chapter 1 and 3. Okay, that's it.